Good morning, good afternoon, good evening, depending on what time you're watching this video. I'm Aboritina Marin, and my other group member is Nalwaga J. Trisila. We are going to give you a brief overview of machine learning. Well, machine learning is a field of study that gives computers the ability to learn from and make decisions or predictions based on data without being explicitly programmed. Basically, it uses data to train, and it will be able to perform actions based on the training it has had or the patterns. And yeah, so why do we use it? When in case we are given a lot of data and we have a problem to solve, we write these machine learning algorithms and train it on the given data. So it will be able to perform the task even though we are not explicitly programming it. So there are two types of machine learning, that is a supervised and unsupervised. So in supervised learning, it uses labeled data. That is, we give it the data, we train it on how to use it, then there's a prediction, or it will give us the result we are looking for. In case we are not confident or we are not satisfied by its performance, we train it again. So an example we have here, we are given this data set, we have values of X and then the values of Y. So this model will train and it will perform. So the problems under supervised learning, we have regression and classification. Under regression, the target value is a numerical variable. For example, temperature, hours, vistas, prices. Then under classification, it's a categorical variable. For example, the yes or no. Moving forward, in unsupervised learning, it uses labeled data set. That is a machine learning algorithm. It learns without any supervision. So it uses algorithms like the clustering and anomaly detection to learn. So under clustering, it will group together features that exhibit the same characteristics. For example, in this example, it grouped the yellow together as well as the gray together. Then in this, it used the closeness or probability to group them. Then the other one is the anomaly detection. In case we had, let's say, a rectangle or a star here, it would be like the unwanted value, or it would be standing out. So that's basically it. So the pipeline for machine learning, we have you get your data, perform EDA, prepare the data for machine learning algorithm, select a model and train it, fine-tune your model, present your solution, then you can launch, monitor, and maintain your system. We are going to look at this in details. So after getting your data, you perform the EDA. EDA is the exploratory data analysis, whereby you're going to examine and summarize the data set to uncover its patterns, characteristics. Basically, you're getting used to the data set. So, well, this should be quick, efficient, and decisive. So how do you do this? You can use the study correlations, like you look for the strong relation between the target variables and features, or you just look for relationship of other features with others as well. Moving forward, you can perform the feature scaling, a technique used in data preprocessing to standardize or normalize the range of independent variables before you can apply the machine learning algorithms. And this is basically formed in two ways, that is the normalizing and standardizing. So normalizing, you're fixing the range of the data between values of 0 and 1 or 0 and -1. Whereas in standardization, you're transforming the data to have a mean of 0 and a standard deviation of 1. So why do we perform scaling? It helps the gradient discrete to coverage faster. And gradient discrete is mainly an algorithm process whereby the learning and training takes place. So when we do the feature scaling, it will help that learning to occur faster. So when to do the scaling, basically when you're studying machine algorithms like the KNN and PCA, we are going to look at this further. And the types of scaling, as we discussed before, the min-max scalar is under the normalizing of data, whereas the standard scalar is under the standardization of data. So you can move forward and do the data cleaning. Data cleaning, just from the name, you're identifying and correcting the errors, because you're basically cleaning so that it's ready for modeling and improving the quality. So how do we do this? You can remove the duplicates, correct mislabeled classes, and handle the missing values. And under handling missing values, you can deal by dropping. You're just going to remove the rows and columns, or imputation. You're going to calculate the mean value and you can add those values. Every machine learning model should have three things, that is the prediction model, cost function, and the optimizer. As we discussed before, under optimizer, you're going to be talking about parameters, and this has the gradient discrete, whereby you're going to measure the difference where training takes place. Basically, you're going to see the difference between your model and how best it's performing to give you the results you're looking for. And cost function is a mathematical function that measures the error difference between the predicted values and actual values in a model. Basically, all these three are working together. And then moving forward, we have the regression and correlation methods. That is, we can have the deterministic models with no randomness and probabilistic models which work with randomness. And the randomness and with no randomness, basically, in case you're given data with certain conditions and you bring back a specific output, that is that no randomness. We are not surprised, we are not shocked. We know when we input this, the result is going to be that. So the types of probabilistic models, we have the regression and correlation models. And regression is basically used for prediction and estimation. Then we can have a quick look at linear regression models. Basically, the relationship between variables is a linear function. Moving forward, we have the estimating parameters. This is under the optimizer. So it's helping us move closer to what we are looking for. Or it's also called the least squares method. Well, this helps us to get the best fit line. And the best fit line is the difference between the actual y values and the predicted values, making sure that it's minimum. The change is not so evident, it's a small change. So we can have a look at the KNN overview. KNN is K nearest neighbor, that is it in full, and it has the parametric and non-parametric models. In parametric models, you know exactly which model you will fit to the data, whereas the other one, it just tells you what the regression should look like. And under the KNN, we have the iris dataset. That is the sepal length and width in centimeters, and the petal length and width in centimeters. Then we can also have a look at EDA on iris dataset. And an iris dataset is very classic. It's just straightforward. Then, well, the steps involved in that KNN algorithm, we have calculate the distance between all the training dataset. I think finding the nearest main KNN steps include you calculate the distance between all the training data and test point. Then you find the nearest k-neighbors by setting these pairwise distances and classify the point based on a majority vote. I'm going to use one of our previous examples to take a look at this. So we have this example. Let's say there was another circle here, and we wanted to determine if it should be yellow or gray. So we shall look at these near ones, two yellows, and then the one that will be close to, there is a yellow, and since it is here, it will be closer to the gray. So you pick two pairs from here, and as well as two pairs from here. But the ones that are closer, that is the color you take. So in case there was another circle here, it would be colored gray. Basically, that's what the KNN algorithm talks about. So in calculating the distance, we can use the equilibrium distance or the Manhattan distance. To the first one, the dimensions measure similar properties, whereas the Manhattan distance, they are not there's a variation. Then we can talk about the Gini impurity. It measures the frequency at which any element of the data set will be mislabeled. Then the entropy is more complex since it uses slow. Basically, you're getting to know your data set. And we can also have a look at pre-pruning. Pre-pruning is implemented by specifying the maximum depth in our implementation or controlling the different hyperparameters in scale-learn implementation. And this pre-pruning cannot be used alone. So it's combined with post-pruning, also known as complexity pruning. So the pros and cons of the decision trees. And decision trees is basically a tree, or we can use it a flow chart that will help us make decisions. So it's easy to implement and visualize since you know this is a yes and a no. So if I take a yes, it will lead me to this. If I take a no, these are my other options. Basically, that's it. Has no assumptions, can easily capture. Then as well, the cons, it's sensitive to noisy data. You have to be decided. Then the small variation in data can result in different decision trees. That's true. Then greedy algorithms do not yield global optimum tree structure. Basically, this is what I was talking about. This could be a decision, then this is a yes or a no. So, you know, if I take this, it will result to this, and if I take this, it will result to this. So decision trees algorithm, you find the best feature, find best split for the best feature, then partition clusters based on 1 and 2. And finally, we are talking about overfitting and underfitting in a decision tree. So underfitting, that model can either model the training data, not generalize to a new data. Basically, this is what we are talking about. You've plotted your graph, and underfitting, this model is here. It has neglected many things or generalized just in between. Then overfitting, the model that fits the training too well, including details and noise. Basically, it's trying to gather everything. Yeah. My other colleague will continue from here.
Good evening. My name is Nel Wagaje, and I'm going to be picking up from where my colleague has left. So we're going to start with ensemble learning, where this is a combination of weak models or base models to make a stronger or more accurate predictor. The idea of ensemble learning and combining the prediction models is to reduce overfitting. What is overfitting? This is where models work well with known data or data they can recognize, but then when new data is fed to them, they start working poorly. So this can reduce overfitting. It can improve generalization where large sets of data or small sets of data are included, and it can increase the overall robustness of the model. And in ensemble learning, there is a problem of we assume that each prediction is independent of each other, which sounds unrealistic. So there are methods in ensemble learning which include bagging and boosting. These methods, they help to solve that problem. And what is bagging? Bagging is the parallel training of models using overlapping, by overlapping them. Or here the definition, like how it says, it's creating multiple models by training on those different subsets of models and then averaging their predictions. And under bagging, there are different algorithms like the random forest and the decision trees. And also bagging may also be known as bootstrap aggregating, because it uses bootstrap. Then we have the boosting, where it's sequential training of models, focusing on solving or correcting the errors that were in the previous models. Yes. We move on to the diagrams. There is an example of bagging. There's an example of bagging where we have said bagging is parallel, and it's a parallel training of models, or it's a separation of models into different sets, and you get feedback from all those sets, and you get the final prediction from its prediction. And then there is also boosting, where we have said that boosting is sequential, or it happens iteratively in order to get the final prediction. Then we move on to the out-of-bag error. The out-of-bag error is the method of estimating the test error in a model built using bagging. Yes. And the test error, an example of the test error is when we use bagging and we are separating those models into different sets, those models are supposed to have components that were in the original set. But then sometimes when those models are separated, some components from the original sample may not be in some of those data sets. So out of bag error is basically to calculate the missing components or the missing data points that were not included in the different sets. Yes, and it's calculated by making predictions on these out of bag samples for each model and then averaging those prediction errors across the models. We move on to bootstrap sampling. Bootstrap sampling is a statistical technique where you create multiple samples from a single data set by randomly sampling data points with replacement. Hence, if they are to get different or multiple samples from a different data set, we are going to have to replace those samples so that when you're creating other different samples, you are able to also include that those data sets or the components are able to also be included in these other data samples that you're creating. And exactly, when each time you draw a sample, you put the selected data point back into the pool, allowing it to be selected again. This may result into overlapping and contain duplication. And bootstrap sampling is used in various machine learning techniques, for example, bagging, like we had said, bagging, another name for bagging is bootstrap aggregation. Move on to the random forest. Random forest is an ensemble learning method that combines multiple different decision trees. Each decision tree in the forest is built on different bootstrap samples of data. So to further increase randomness in random forest, each decision tree that is generated is split into a subset of features, and that is considered as splitting. And the final prediction is made by aggregating the predictions from all the different individual decision trees. And these decision trees are mainly known for their high accuracy and ability to handle high dimensional data and resistance from overfitting. There is an illustration of random forest. As you can see, there is the first decision tree, the second one, and the third one, and then we get the average of all the predictions and get the final result. There are pros and cons from the random forests, and among the pros, it works well with nonlinear data. It lowers the risk of overfitting. It runs efficient in a large data set. If the data set is large, it can be separated into different decision trees, and you get a prediction or a final prediction from the different different decision trees. Then it's robust to outliers. Outliers is data that is different from the rest. It helps to include those outliers, and it makes handling those outliers manageable. Then we have the cons where it's biased while dealing with categorical variables. If the variables have a lot of categories, it may be a little bit biased. There is slow training because having to separate all those different a data set into different decision trees is time wasting. It's not suitable for a linear method with a lot of sparse features or feature or data set with limited features or small features, then it's a greedy algorithm, hence it does not yield the global optimum because it chooses the very best option. We are contrasting between bagging and boosting. As I had said, bagging is parallel. It's a parallel training of models, of different models. And the final prediction is an average of the predictions of all the models, while boosting is sequential and it happens iteratively, where it focuses on correcting the errors made by the previous models. We move on to the support vector machine, where the support vector machine is an algorithm that is used to find the optimal hyperline that best separates data points of different classes. Under the support vector machine, we have the support vector machine hard margin, where the data is perfectly separated by the hyperline. And we have the soft margin, where the data may not be perfectly separated due to outliers or due to noise. There is a diagram showing the support vector machine hyperline example. We move on. Under the support vector machine, we have linearity, where it uses a linear hyperline to separate the data. But through the kernel functions, it enables data that seems nonlinear and separable and transforms it into a linearly separable data. Then we have regression, where regression it uses a function that best fits the data points in order to find the hyperline that separates it best. We have the SVM cross-validation, and the SVM cross-validation is used to evaluate and tune the SVM model. And an example is the k-fold, where the data is divided into k-folds, and the model is trained for k-1 folds and tested on the remaining folds. And then the process is repeated until the average performance of the folds is estimated. Yeah. Moving on, we move on to the difference between machine learning. My colleague had talked about machine learning and with data standardization. Data standardization is where the data is transformed to have zero mean and unit variance, or the data is transformed to be on the same level. This prevents features with larger scales from dominating the learning process. Under data standardization, we have an algorithm that uses data standardization, and that is the k-mean algorithm. Yeah. And under the k-mean algorithm, we have this is where data is clustered. It is separated and it's put into groups based on its similarity. Yes. And there is a diagram showing the k-mean algorithm. The k-mean algorithm has its strength where it's relatively simple and efficient to implement because you're just separating data into clusters according to their similarities. It can handle large sets of data because large sets of data can be broken down into clusters, can be used for both clustering and dimensionality reduction. Its weaknesses: it's sensitive to the initial placement of centroids, assumes clusters are spherical and of similar size, yet they may be of different size, may not perform well with non-linearly separable data, and it requires specifying the number of clusters beforehand. Lastly, we move on to the PCA, also known as the principal component analysis. The principal component analysis falls under unsupervised learning, which deals with unlabeled data, where the goal is to find patterns and structures within the data. And principal component analysis is powerful in such a way that it reduces the number of features that is in the data, but then it keeps the most important information in the data. And there are its limitations, where it assumes linearity in the data. It may not preserve the local relationships between the data points, and it's sensitive to outliers. And its applications, it's dimensionality reduction, data visualization, noise reduction, where it removes noise and irrelevant information from data, and its feature extraction. Implementation, under its implementation, we have image compression, data preprocessing, and visualization with regression of analysis. Lastly, we have the feature scaling, where it enables that data is put at the same level. And that's where standardization and normalization fall. And basically, lastly, this allows all features to contribute equally to the analysis. Yes. Thank you. That's the end of my presentation.